Are there any questions about the last lecture? Yes, sir.
After you proved the low energy theorem, you extended it to the case of neutrons instead of protons.
Yes, the only difference there is that F1 of 0 is 0.
Yeah, I can see why that was.
Because the neutron is electrically neutral. F1 of 0 measures the total charge. There is no need to put in a neutron charge renormalization.
Well, it's appropriate to saying that the three-point vertex only depends on sigma mean times k mu, right?
Well, look, if we try to prove the Ward identity for the neutron, the commutator term, the neutron field is electrically neutral. It doesn't gauge transform at all. So what you get is that gamma mu, the three-point function, vanishes for a zero momentum transfer.
But how can you show that all graphs proportional to gamma mu must transform?
Because from the Ward identity. Remember, for the proton, we had something like, that was our short notation for the three-point function. 0, that's the photon momentum. I don't remember whether this is plus IE or minus IE. Sorry, no, it goes the other way. That's what I remember. Equals do you remember deriving that equation? Okay, now I can run through exactly the same arguments for the neutron. Okay, except now this will be 0. Whoops. Oh-ho. He's on the other side. I had it right the first time. Sorry. Yes, that's right. This to lowest order is E gamma, little gamma mu, and this to lowest order has no E in it. I've got it on the right side now. Okay. I mean, if the charge is the electron charge, bare charge is the electron charge, the renormalized charge, which is connected to F1 at 0, is the electron charge. If it's a quarter of the electron charge, it's a quarter of the electron charge. If it's 0 times the electron charge, it's 0 times the electron charge. Okay. Equivalently, E for any particle, E is a universal factor, Z3 the minus 1/2, the plus 1/2, times E naught. And if E naught is 0, E is 0. Okay, are you happy, or do you think I'm swindling you?
Yeah.
Yes. F1 of 0, if I take the... It doesn't couple to the neutron at 0 momentum transfer. The neutron certainly does have a non-zero F1 form factor, and it has a non-zero F2 form factor even at 0. The statement is simply that the neutron is an electrically neutral system, so whatever it happens virtually to it, which decays into a proton and a pi minus, it'll still have net charge 0. Okay, however, in the process of decaying from a proton and a pi minus, or virtually, and coming back again, those proton and pi minus may be whirling about itself, and it may have a magnetic moment, and indeed it does, and it may have an electric quadrupole moment, and indeed it does. But what it doesn't have is charge. Not quadrupole. Can't have anything. It can have a charge radius. It can have a charge radius, right. If it had a higher spin, it could have an electric quadrupole moment, but as you're quite right, a particle spin 1/2 cannot have a quadrupole moment. Okay, it can have, its charge distribution can be spread out, but the net charge has to remain 0. And in terms of form factors, that's the statement that F1 vanishes at 0 momentum. Are there other questions? If the answer wasn't clear, ask the question again. No, everyone is happy. All right. Now, last lecture we were discussing the phenomenology of eta decay. I pointed out from what we already knew about the electromagnetic interactions. Let me write down what we had. Eta is a particle with J to the PG equals 0 minus plus, negative parity, positive G parity. And therefore, its decay, eta into 3 pi's, must be into an I equals 1 state, of course, with I sub z equals 0, because we demonstrated that the only part of the second order electromagnetic interaction that had the possibility of changing G carried delta I equals 1. Therefore, the final state must be the I sub z equals 0 member of an isotriplet. This enables us to connect the decay eta into 3 pi naught and eta into pi plus pi minus pi naught by a little isospin Clebsch-Gordonry, and I'd like to look at that process in some detail just so you get some idea of what sort of restrictions this sort of analysis makes. For variables, I'll have to introduce a set of variables for the 3 pion system. As we showed in our analysis last semester of the kinematics of 3-particle decay, when we talked about Dalitz plots and such things, a very convenient set of variables is the energies of the 3 pions. Those are, of course, redundant. The mass of the eta, which I see from my notes, and it'll be important, is around 548 MeV. These are 3 redundant variables constrained this way, and thus the allowed points can be represented as points in a diagram in either the E1, E2, or E1, E3, etc. plane, which form the so-called Dalitz plot. For our purposes, it will be convenient to introduce new variables. Epsilon I equals EI minus M eta over 3, and then epsilon 1 plus epsilon 2 plus epsilon 3 equals 0. And the center of the Dalitz plot, assuming we ignore the electromagnetic mass differences between the pions, the center of the Dalitz plot is the point where all the epsilons vanish. We will also, for the 3 pions, treating them for the moment as distinguishable particles, which we certainly can, except for a set of measure 0 in the Dalitz plot, they're labeled by their energies, we will introduce 3 isospin 3 vectors, E1, E2, and E3, just like the polarization vectors we had for photons, except for this case they label the direction of the 1-particle states in isospin space. The amplitude for decay, I perhaps should say, if it's a charge 0 state, a pi naught, E equals EZ. And if it's a pi plus or minus, E equals EX plus or minus I EY over root 2. Now, the first question is, how many amplitudes can we construct that are isospin 1? This is pretty easy. Labeling a representation of the rotation group just by its spin, we know if we put together 2 pions, this is without worrying about statistics or anything, if we put together 2 pions, 1 times 1, we can either construct a state of isospin 0, or of isospin 1, or of isospin 2. Therefore, if we put in a 3rd pion, we get isospin 1 3 times, once from each of the factors. I don't care about the non-1 part. Thus, we should be able to construct, if we fixed epsilon, 3 3-pion wave functions, 3 functions linear in the 3 E's, that transform like isospin 1, that transform like a vector under the isotopic rotations. It is easy to see what those functions are. E1, E2 dot E3, for example, is a vector. And of course, it could be multiplied by a function, epsilon 1, epsilon 2, epsilon 3. I could then have, this is a vector amplitude, if it could go into all three isospin channels. Likewise, I could have E2, E1 dot E3 times another function. I'll keep that out for the moment because I want to make a remark before I write it down. Sorry, E1 dot E2. Those are obviously three linearly independent amplitudes that all transform like vectors. The generalized exclusion principle tells us that the total amplitude must be antisymmetric, must be fully symmetric when I interchange both space and spin, which doesn't exist here, and isospin variables. So the first thing I note is that f of epsilon 1, epsilon 2, epsilon 3 must equal f of epsilon 1, epsilon 3, epsilon 2, because this thing is already symmetric when I interchange E2 and E3. And finally, these must be the same functions, f, in this case with epsilon 2 in the preferred position, and in this case with epsilon 3 in the preferred position. But the same function, f. I've now constructed the most general wave function, or decay amplitude, as you will, that is, has the proper isospin transformation properties and is consistent with Bosch statistics. Of course, this is a vector of amplitudes. We actual decay final state, because electromagnetism preserves I sub z, is the I sub z equals 0 member of this triplet, which we project out by, of course, dotting onto a unit vector in the z direction. Now, are there any questions about this? The next stage in the analysis is going to make an approximation which, as you will see, will introduce a small error, but one that is useful for getting information. The epsilons are all fairly small. Even in the case of 3 pi naught decay, the mass of the neutral pion is 135 MeV. And thus, the mass of 3 neutral pions, even if the E equals mc squared energy of 3 neutral pions, is 505 MeV, which means we have only 43 MeV available for the decay. That has to be split up somehow among the 3 pions. In the case of the charged pion decay, pi plus, pi minus, pi 0, the situation is even worse, or even less energy, because the charged pions are on the average of 4.5 times, the charged pions not in the average, are 4.5 MeV greater in mass than the neutral pions, so we have 9 MeV less left. This means that, in fact, the effects of electromagnetic mass differences, which are normally negligible, are in fact on the order of 10 or 15% on this process, because they cut down the available amount of phase space by 10 or 15%. There are, of course, large effects if you have very little energy available, and even a small mass difference can be a large effect. But I'll ignore that and live with a possible 10 or 20% error. Treat the masses as if they were the same. However, what I will not ignore is that because there is a small amount of energy available for the decay, the epsilons tend to be small, and therefore I will make a linear approximation for the functions f, that is to say in gamma, integral over the Dulles plot, that complicated curve which we worked out last semester, d epsilon 1, d epsilon 2, epsilon I, or epsilon 1, it doesn't matter, it's all symmetric, epsilon 1 squared. I'll only expand f to first order in epsilon, and then ignore in computing the total cross-section's quadratic effects, because I expect epsilon to be small compared to a typical strong interaction mass over the entirety of the Dulles plot, and therefore effects of order epsilon squared should be negligible. Thus I will approximate f equals a constant, its value at the center of the Dulles plot, plus b epsilon 1 plus c epsilon 2 plus epsilon 3. These must occur with the same sign because epsilon, with the same coefficient, because it must be symmetric under interchange of epsilon 2 and epsilon 3, plus order epsilon squared, which I am neglecting by assumption. Since epsilon 1 plus epsilon 2 plus epsilon 3 equals 0, I can write this as a plus b prime epsilon 1, since epsilon 2, where b prime is b minus c. I said by assumption, I should have said by construction. Any questions about this approximation? We certainly make some error by it, and we'd expect that, as I say, to be a 10 or 15% error. If we have a lot of data on eta decay, we don't have to make this sort of assumption, but I want to get a result for the total rate, and this would require such an assumption. Now, such an approximation. Now we're in business. I'll first consider eta into 3 pi naughts. In this case, E1 equals E2 equals E3 equals E sub z. Thus, the E factors in all 3 terms contribute 1, and I have a decay amplitude, which is A plus B prime epsilon 1 plus epsilon 2 plus epsilon 3, which is otherwise known simply as A. In the linear approximation, the distribution of points in the Dulles plot is completely flat for 3 pi naught decays, independent of position in the Dulles plot. For eta into pi naught, pi plus, pi minus, I choose, of course, doesn't matter how I choose it, I'll choose E1 to be EZ, E2 equals EX plus I EY over root 2, and E3 equals EX minus I EY over root 2. Thus, the first term contributes to the amplitude. EZ is orthogonal to E2 and E3, and I obtain the decay amplitude is just the first term, A plus B prime epsilon 1. Thus, the distribution in the Dulles plot in the linear approximation is symmetric between independent of the pi plus and pi minus energy, but depends linearly on how much energy is given to the pi naught. Martin, you have a question, or you're just scratching your head? Indeed it should. Thank you. And it's a good thing you caught it. I would have made a mistake. Now let's actually compute the total decay rates. At first glance, it looks like we can't compare the total decay rates because one of them depends only on A and the other depends on both A and B prime. Let's do what's at hand, gamma eta into pi plus pi minus pi naught equals integral over the Dulles plot, the epsilon 1, the epsilon 2, how we do it doesn't matter, which pair we choose, times a numerical constant, which isn't going to be particularly relevant, a plus b prime epsilon 1 squared equals integral a squared plus what is it? A star b prime plus b prime star a times epsilon 1 plus order epsilon squared, which, consistent with my previous approximations, I neglect. Now, the Dulles plot, we're ignoring the mass differences, so the Dulles plot is complete between the three pions, so the Dulles plot is completely symmetric under epsilon 1, epsilon 2 interchange. Therefore, the integral over the Dulles plot of epsilon 1 is the same as the integral over the Dulles plot of epsilon 2 or epsilon 3, or equivalently 1/3 the integral of the sum. But the sum is 0, and therefore its integral is 0. And therefore, this term is in fact 0. It integrates to 0. Thus, we see that although in our approximation, although we see linear terms in the distribution of points in the Dulles plot, the actual total number of points in the Dulles plot is unaffected except by quadratic terms. Points are shifted in one side or the other of the line where where epsilon 1 equals 0, but the same number go to one side as go to the other. Now, for the 3 pi naught decay, of course, it's much more straightforward. Round 2, just a squared, nothing else, with a 9, and with a 3 factorial, because we don't want to count the same experimental event 6 times. Thus, this is 3 halves gamma eta into pi plus pi minus pi naught. Thus we have obtained our prediction, which, as I say, since we are ignoring the mass differences, which make around a 10% difference in available energy, we would expect 10 or, well, I haven't done the computation of phase space, maybe a 10 or 15% error in this prediction. The observed experimental numbers, I mean, that's something that's sort of trivial to fix up. You have to figure out how much phase space you got in the 2 cases. And, yes? Sure. It's 1/3. Since if we ignore the mass differences, the Dulles plot is completely symmetric under permutation of the 3 particles. But that's 0. The experimental numbers are, oh, I can't write them down here. People will go crazy craning their necks. I'll write them up here. Actually, the experimental numbers for the total decay rates are very unreliable. The total decay rate of the eta is difficult to measure, but the branching ratio is well known, except it's not well known on this piece of paper. It's well known on this one. Equals, according to my wallet card, 23.9 plus or minus 0.6 over 30.0 plus or minus 1.1, which is an agreement within the expected theoretical error caused by neglecting the pion mass differences. Any questions? This is a number that should be 2/3 theoretically, and is closer, and is 20% off or something like that, depending. Yes? That's right. Well, I don't know. I was trying to look it up in the literature and I couldn't find it. Okay, how it goes with available. The first effect you would take account of in the crudest way. First, the linear approximation may be bad, but as I recall, it's not. If you actually look at the density of points in the Dahls plot, the linear approximation fits them very well. The first effect one would have to look at, I guess, would be to see how three-body phase, the size of the Dahls plot changes with the available energy. Okay, and make a correction for that. You just have less phase space to decay into. And I regret to admit I was too lazy to do that computation. I couldn't find it in the literature. It's fairly straightforward. Although, that would enhance the 3 pi naught decay because there's more phase space around. The pi naughts are lighter. Okay. Which is the wrong direction, isn't it? Oh. That's right. Yeah. That's. But I haven't looked at that. The big problem in eta decay is not this part, as I recall. This there, I'm not giving you any deep insight. I'm just remembering what I learned from listening to seminars with half an ear. The big problem in eta decay is not this, but experimentally determining the absolute rate, which is done very trickily, using something called the Primakov effect, and I can't even remember what it is. It involves eta production from a photon hitting a nucleus, yes? In the Coulomb field of a nucleus. And which is a tricky experiment, and the results keep fluctuating. And also the big theoretical problem is that unless the experiments are very badly wrong, the result is the amplitude is embarrassingly larger than it should be on the basis of crude estimates of the size of an electromagnetic effect. Okay. That terminates the last lecture. We forgot to, whoever is picking these things up and storing them in the Science Center, forgot to pick them up last time, so here it is. And we now begin the lecture properly allocated for today, which is, that is to say, we begin a new topic. I don't expect to finish the complete lecture today. And this new topic is SU3. We've seen that we can get a lot of results about processes that have the strong interactions entering into them in a complicated way, even in almost total ignorance of the strong interactions, just by exploiting the known symmetries of the strong interactions and the known symmetries of the other interactions, known transformation properties of the other interactions under the strong interaction symmetry group. And indeed, the second half of last lecture was a collection of such examples. Now, in around the mid and late 50s, some people began thinking, both Murray Gell-Mann and Julian Schwinger began thinking, very smart people, that maybe one could play this game even further. What principally made them think this was, firstly, the establishment by Gell-Mann and Nishijima a few years earlier of strangeness or hypercharge, which indicated that isospin worked perfectly well for all those new particles that had been coming out of the new generation of high-energy machines, low-energy machines by today's standards, exotic particles like lambdas and sigmas and things like that, all K-mesons, strange objects, had all fit in with isospin, and they were beginning to assemble them in families. And in particular, there seemed to be 8 so-called baryons. particles that were pretty much like the nucleon. They had spin 1/2, baryon number 1, parity plus, to the extent one could assign a parity, and they had different isospins and hypercharge, and they were rather close together in mass by the scale of these things. I'll write them with the heaviest one on top, the cascade doublet. Write down their total isospin and their total hypercharge. There were 2 of these. The hypercharge was -1. They came in a neutral and a negative. They still do. Sigma triplet, 1, 0. Lambda, 0, 0. And, of course, our old friend, the nucleon, 1/2, 1. These particles seem vaguely similar in their properties. As I said, they seemed at that time, as far as the experimental evidence went, to have the same parity. They unquestionably all had spin 1/2. They unquestionably all had baryon number 1. And they were relatively close together in mass, the mass splitting between the heaviest and the lightest being on the order of 15 or 20% of the mean mass of this collection of particles. This led to an idea. Back in the 30s, Heisenberg and friends had suggested that if you neglected electromagnetism and took then the strong interactions, all that remained, the nuclear forces they were called then, the world would be much more symmetric than it was in reality. In particular, it would possess isospin symmetry. Therefore, Schwinger and Gell-Mann, at around the same time, said maybe the same thing could be done with the strong interactions. Maybe they split, hypothesis, into 2 families. Very strong and medium strong. And if one were to ignore the medium strong interactions, which of course a much bolder step than ignoring electromagnetism, perhaps just as when one ignored electromagnetism, the neutron and proton have the same mass. When one ignored the medium strong interactions, all 8 of these particles would have the same mass and be part of a degenerate multiplet because there was a larger symmetry group. Wouldn't be as good asymmetry as isospin. A 10% splitting, a 10 or 20% error is much more of an error than a 1/10 of 1% error or 1% error, but still better than nothing. Hell of a lot easier to try this idea than to try solving the dynamics of a strong interaction process. Well, so it was clear, although nobody spoke that mathematical language at the time, what the problem was. First you want to guess some group. I'll call it G, some internal symmetry group that, of course, contains the ordinary isospin hypercharge group. It's got to be inside there because you certainly want the new symmetries when you ignore the medium strong interactions to include the old symmetries when you don't ignore them. First criterion on G. Second criterion on G. G must have an eight-dimensional, a unitary representation, and irreducible representation at that. So you can accommodate the 8 observed baryons in the representation, a single representation of G, and because that representation is irreducible, they will all be forced to have the same mass. Otherwise, SU2 cross U1 would be a solution of the problem so far. Yes?
Could you also believe that you had a 7 and a 1?
Yes, I will talk about that momentarily. C, of course, when you reduce G to the SU2 cross U1 subgroup, when you restrict yourself to that subgroup, you don't just want an 8-dimensional representation, you want an 8-dimensional representation that decomposes into these observed particles, exactly not 2 isoquadruplets. That's not an answer to the problem, but precisely this. That is to say that on the 8-dimensional representation must go into cascade, lambda, sigma, and nucleon. Isospins and hypercharge that can be identified with those. Well, at that time, nobody knew any group theory, except Wigner, and he wasn't talking. And so they just sort of guessed it. They flailed around. Schwinger and Gell-Mann made the same guess, called global symmetry. And there wasn't much data at the time, so it wasn't immediately clear, but after a year or two it became clear it was dead wrong. And then people tried other things. There was a whole school of thought. Saul Barchet, who said the lambda had opposite parity from the sigma. There were just bad experiments, and that we should look for a seven-dimensional representation. The lambda was just coincidentally sitting there in the middle. And there were people who fiddled around with the idea that there were maybe there were 9 particles, and we just hadn't found the 9th one yet because it was a little bit heavier than the cascade, and we should be looking for a group with a 9-dimensional representation. And people played this game for a while, but it became clear that there weren't any other, and it's certainly very clear now in retrospect, there aren't any other particles around the same mass range. And insofar as the weak interactions allow us to define relative parities, the parities are all the same. And therefore, the problem as originally formulated, or as formulated on the bottom of this left-hand board, is the correct way of formulating the problem. Now, many years later, around 1960, Gell-Mann, in fact, guessed the right group. It's a very interesting anecdote because I was present at the time as a graduate student at Caltech. I had at that time, Gell-Mann and Shelley Glashow, who was a postdoctoral fellow, were working on a Yang-Mills theory, not knowing what it was good for. It wasn't that Steve Weinberg discovered that. They were working on Yang-Mills theory, and they wanted to learn some Lie group theory, because that comes in. At that time, considered, research like fiber bundles, not anything any respectable physicist knew. And in fact, Moore came into my office because at that time I had a totally undeserved reputation for mathematical sophistication. I could tell an epsilon from a delta. Said, do you know anything about Lie group theory? And I said, who, me? I can tell an epsilon from a delta, but that doesn't mean I'm Andre Vey. Of course not. Well, fortunately at that time, the mathematics department was in the same building as the physics department. And Murray went upstairs and found a mathematician who was willing to talk to him, who said, there is this book in French that's a précis of the main results of Lie group theory called the Seminar Sophus Lie, and take it out of the library and read it. Murray is very fluent in French, so he did just that. And 2 days later, he came in great excitement and said, there is a group with an 8-dimensional representation called SU3. And we said, SU3, 8-dimensional, go away. Well, of course, he hadn't gone bananas. It turned out to work, as we all discovered very shortly. And that was how it, in fact, happened historically. Then, afterwards, there's also Yuval Ne'eman, who made the discovery independently. Well, that's also an interest. I'll tell it. Who cares if the lecture runs over? Yuval had been trained as an engineer and had wanted to become a physicist since 1947, but the Arabs kept keeping him from going to graduate school. And finally, after being acting head of Israeli military intelligence during the Sinai campaign and such things, he was able to talk the Israeli general staff into getting him a half-time job as military attaché in London. And half-time he went to graduate school at Imperial College under Abdus Salam. And at first the British Foreign Office was reluctant about giving him permission to do this because they had a confusion between high-energy physics and building bombs. They thought he wanted to be a spy. But he finally got the head of the general staff, who at that time was Dayan, to write a letter explaining that it was really all okay. And he has subsequently described himself as the only graduate student ever accepted by Salam on the strength of a letter of recommendation from Moshe Dayan. And Salam put him on this problem, and he also came up with SU3 at around the same time. I also remember that, Murray rushing in with a preprint and saying, some Israeli colonel has made the same discussion. Okay, those were enough for stories of my youth. The golden age of physics is 23, and but afterward, people began to wonder if something had slipped through the net, and began looking at the problem in a systematic way, of course too late, as always, and investigating what were the mathematical answers to this problem. And that's why I'd like to do it in pseudo-historical order, tell you the mathematical answer to this problem, not prove it, because it's neither a sophisticated proof, it's not a sophisticated proof, it's just a tedious one, and then systematically explore the possibilities given by this mathematical answer and see that nothing works except SU3, and then we'll spend a lot of time on SU3. The answer is as follows. Every G satisfying these criteria contains, as a subgroup, either two possibilities, a group called minimal global symmetry, which I will describe, but I'll just write it down. The original symmetry of a suggestion of Schwinger and Gell-Mann was called global symmetry, and later Yang and Lee pointed out that it contained a subgroup that was gave you almost as many results and almost as disgusting. I'll just call this group G0. That's ad hoc notation, it's not. Or B, SU3, the group of all 3x3 unitary unimodular matrices. Of course, this is not an exclusive possibility. One answer to the problem is obviously SU8, the group of all 8x8 unitary matrices, and that contains everything that satisfies the problem. But they all either contain minimal global symmetry, which I will shortly describe, or SU3. Therefore, we will systematically investigate these two possibilities. I first will describe minimal global symmetry. G0 is the product of three SU2 factors. That's why people guessed it, because at that time the only group they knew was isospin. Thus, its generators can be written as three commuting triplets of isospin generators, I1, I2, and I3. I will now describe how the isospin and hypercharged subgroups are embedded as a subgroup. I is simultaneous I1. Isospin is simultaneous rotations in the 1,2 isospin space, and Y is 2-ice, the Z component of I3. These are commute and obviously obey the SU2 cross U1 algebra. The representation D of G in which the 8 baryons are to be assigned is in fact a reducible representation of this group. A general representation is of course labeled by 3 spins, S1, S2, S3. For the 3 isospins, just like 2 spins came in our analysis of the Lorentz group last semester. And the representation in question is the direct sum of D 1/2, 1/2, 0 plus D 1/2, 0, 1/2. This, of course, G0 is therefore not a solution to the problem because this isn't irreducible, but as I say, the mathematical theorem says it is contained in many solutions to the problem, not that it is itself a solution.
Why do you want the mixing of
You'll see. It'll come out in a moment. If I reduce to isospin and hypercharge alone, in this case, since I have the sum of two isospin halves, added together, I obtain isospin 1 and isospin 0. So I obtain from here both, of course, with y equals 0, since this is a singlet under the third isospin group and therefore carries 0 hypercharge. This is, of course, the sigma and lambda. In this factor, I only have isospin 1/2, 1/2 plus 0, so both factors have I equals 1/2. But because y can have, which is iz, can have the two values plus 1/2 or minus 1/2, I have y equals plus or minus 1. And that's the nucleon and the cascade. Indeed, the first thing when people looked at this pattern was they said, well, obviously there's some sort of reflection or something at work here. The nucleon and the cascade, there must be some symmetry operation that exchanges them and changes the sign of hypercharge. Look, they look the same. They're at opposite ends. Flip it around. And in fact, that turned out, as I will demonstrate immediately, to be a dead wrong guess. But it was a very plausible one, and it's what led to this group. Now, this group is, as said, in direct contradiction with many experimental results, although, of course, none of them were known at the time it was proposed. The easiest way to establish a contradiction is to define a group element called R, which I will do. It's an element of the group. E to the I, pi, I sub y, 3. It's a rotation by 180 degrees about the y-axis in the third isospin group. Therefore, R commutes with isospin, because that's just from the first and second, but changes the sign of hypercharge, because that's proportional to IZ3. From the existence of this single group element, one can drag an almost endless string of contradictions from experiment. For example, since there is supposed to be a symmetry group element that doesn't do anything to isospin but changes the sign of hypercharge, for every hadron, stable or unstable, with a given hypercharge, non-zero, there must be another hadron of approximately the same mass within 10 or 20% with the opposite hypercharge, obtained by applying R, which changes the sign of hypercharge. And of course it commutes with nucleon number, so it's not the antiparticle, it's something else. Now there's the well-known delta, or n star, 1238, that big fat resonance in pion nucleon scattering with I equals 3/2 and y equals 1. So there should be a big fat resonance with I around the same mass with I equals 3/2 and y equals minus 1. And you may search your Rosenfeld tables to your heart's content, and you will not find such an object. It is not there. Of course, at that time, they didn't know it wasn't there because, you know, looking in the cascade channel wasn't easy. The cascade had just been discovered a few years before. Is that clear, how this contradicts? Secondly, we can use the same analysis about magnetic moments that was described last time. The lambda you see is a singlet under the third hypercharge, under the third isospin. So in particular, R doesn't do anything to the lambda. If I have a 1 lambda intermediate state, with this is spin and space indices, I simply get the same state. On the other hand, if I look at the y component of the electric current, the part that comes from J mu y, R changes the sign of that. because it changes the sign of y. Within a lambda state, if I look at the electromagnetic current, only J mu y contributes by isospin. J mu I sub z is an isovector and cannot have a matrix element between two isospin 0 states. But by R, this is 0, because I apply R adjoint here and R adjoint here. The lambda doesn't change sign, the current changes sign. Thus, I am led to the conclusion that the magnetic moment of the lambda must be 0. Now, of course, that magnetic moment of the lambda wasn't even measured until 1963, so that didn't shake anyone up at that time. But now it is measured and is known to be on the order of half the neutron moment, a typical hadron magnetic moment, not particularly small in any reasonable sense. And I could go on forever. You could allow yourself to run through the Rosenfeld tables if you want an amusing exercise, demonstrating that any higher symmetry theory, any theory about a greater symmetry that includes a hypercharge reflection operator of this kind, is guaranteed to be cooked. It's just, the universe is not symmetric under changing the sign of hypercharge and not changing the sign of isospin and nucleon number. Thus, G0 is out. And if you therefore accept this theorem, which I have told you without proof, our last best hope is SU3. Either that works or the game is up. Well, of course it does work, otherwise I wouldn't be giving this lecture. And therefore, rather than directly doing things for SU3, I'd like to devote the remainder of this lecture and portions of next lecture to mathematical preliminaries in which I work out the theory of the representations of SU3. And then after we have our mathematical machinery set up, it's worth the effort because I know in advance it's going to be good for physics, I'll then start applying it to a variety of physical problems. And there's a group and an 8-dimensional representation and embedding of SU2 cross U1 in the group. And it's extremely tedious. You just look up books on Lie group theories and you count up all the Lie groups that have 8-dimensional representations or 4-dimensional representations, because it could be two 4s connected by a discrete element. And you write them down and then you figure out all possible ways of fitting isospin and hypercharge in. And you are left, I believe, with 13 possible groups. And then you figure out which contains which one. You make a big, my thesis, you make a big diagram with boxes and trees, and you find that they all end up either on this thing or on SU3. It was dull. I did it, believe me, it was dull. At the end of it, though, I knew Lie group theory. If I had known Lie group theory a year before, well. Now, so I will begin by making some preliminary remarks about the representations of SUN, although I certainly won't classify them for arbitrary n. And then I will specialize shortly, first all the way down to SU2, just so we can check that the methods I will suggest work, in a case where we already know the answer, and then to SU3. This is, in fact, the method of discussing the representations introduced by Hermann Weyl in his book on the classical groups. We already know SUN is a group of all n by n unitary unimodular matrices, unitary matrices with determinant 1. And we already know one representation of SUN, to wit, an n-dimensional representation, where things are represented by the matrices themselves. We have a complex n vector x, and under the action of the group, x goes into ux. It will be convenient to write this out in index form as if these were Lorentz tensors, except they're not. They're SUN vectors. And write this as xi goes into uij xj, where for the moment the reason I put one of those indices upstairs is sheer perversion, but I'm adopting the summation convention. Another representation we know offhand, the complex conjugate. If we have a representation as complex conjugate is always a representation. The complex conjugate matrix may or may not be equivalent. It turns out it is equivalent representation for SU2, but not for SU3 or higher SUs. And I will write that out in the following way using an upper index here. Yi goes into U star ij yj, where by definition U star ij equals U upper I lower j. Whoops, sorry, got it backwards. This use of upper and lower indices, of course, mimics the notation in ordinary four-dimensional tensor analysis, and this mimicry is done for a reason, is to remind you that if I take one vector that transforms according to the representation, the first representation, the other according to the conjugate representation, and sum them up, then the summation of upper and lower indices is an invariant operation. That's simply the definition of a unitary matrix. It is precisely the object that preserves that quadratic form, that bilinear form. Now, thus I have two kinds of vectors, upper index vectors and lower index vectors, just as an ordinary tensor analysis. What I don't have is, of course, a metric tensor that enables me to operate in lower indices. At this level, they're just two different kinds of objects that transform in two different ways. By taking products of these objects, I can, of course, construct tensors, more complicated representations that are have m upstairs indices and n downstairs indices, and all the upstairs indices transform as if they're upstairs vectors, and all the downstairs indices as if they're downstairs vectors, and I'm too lazy to write it out because you all know how it goes. There's a u for every downstairs indices and an index, and a u star for every upstairs index. These tensors form a bunch of representations of our group SUN. A lot of them. Of course, they're not guaranteed to be irreducible, but they are guaranteed to be representations. There are all sorts of manipulations we can do on these tensors that are invariant operations. For one thing, something that is invariant is symmetrizing or anti-symmetrizing on a pair of upper or lower indices. That's because any two upper indices transform in the same way. So if you break a tensor up into a part that's symmetric on the first two upper indices and a part that's anti-symmetric on the first two lower indices, as I say, first two upper indices, then if you make the transformation, the symmetric part goes into something symmetric and the anti-symmetric part goes into something anti-symmetric. Likewise for lower indices. On the other hand, it is a no-no, strictly forbidden, to symmetrize between an upper and a lower index. Well, it's allowed, but if you make a transformation, that symmetry won't be preserved because the upper index transforms differently than the lower index. Also, as we see from this example, another symmetric operation is summing an upper and a lower index. You can't sum two lowers because there ain't no metric tensor, and you can't sum two uppers, but you can certainly sum an upper and a lower. There are also some invariant tensors around. Some tensors which, if transformed according to the rules, don't transform at all. One is delta ij, the Kronecker delta. That, of course, is just a statement that our matrices are unitary, or equivalently that summing an upper and a lower index is an invariant operation. The other one, which comes from the fact that the determinant is 1, is the epsilon tensor. Either this one, where this n here is actually the number of element, the n in un, or this one. Because you know when you make such a transformation, the epsilon tensor goes into itself times the determinant of the transformation, and the determinant of u is 1, as is the determinant of u star. Okay, is everyone happy with this? Now, I will now explain Hermann Weyl's program, which for all cases except SU2 and SU3 requires exquisite knowledge of the representations of the permutation group, but doesn't for SU2 and SU3. Hermann Weyl's program is to attempt to find all the representations in the following way. Take all these tensors, symmetrize and anti-symmetrize, and multiply by epsilon tensors like crazy until you've gone as far as you can, being as smart as you can, being Hermann Weyl. And you think you've done, take out all the traces and everything, you think you have constructed invariant subspaces with the space of n-component tensors, n-index tensors, that are irreducible, you hope, crossing your fingers. Okay? You then strive desperately to prove that these are, in fact, irreducible representations, that not some clever graduate student won't come along and say, hi, you forgot about multiplying this index by that index, and you could get an even smaller subspace. You prove that they are irreducible, and you prove that they are, in fact, a complete set of irreducible representations, and thus construct a complete set of irreducible representations for SUN. Okay? That's the program. You take the tensors, you symmetrize and anti-symmetrize until you break them down into what you hope are irreducible objects, and then you try and prove they're irreducible. The amazing thing is that the program works if you're Hermann Weyl, and in fact, if you are, even if you're not Hermann Weyl, for SU2 and SU3, it's pretty easy to make it work. To demonstrate that, I will work out the program for SU2. Is it clear to everyone? It's silly to fall off the train now, because if you don't understand the basic ideas, you're going to be bored for an hour and a half. But that's not the remainder of this lecture. I mean this lecture and part of next one. So we'll start out in the simplest case, SU2. Now, in this case, the epsilon tensor has only got, either of the epsilon tensors has only got two indices. And that means we can use them to raise or lower indices. Just like the metric tensor. Of course, it's not like the metric tensor. It's antisymmetric, but it's still an invariant object with two lower indices. Conversely, y upper j is epsilon I lower j, I guess with a minus sign. Whoops, sorry. What? Did I do it wrong? Yes, I did it very wrong. Thank you. So given any tensor with a bunch of upper and lower indices, we can always reduce it by lowering indices with the aid of the epsilon tensor to a tensor with only lower indices. So our first step is very simple. We need only look at a tensor with only lower indices. They're going to contain everything because everything else is equivalent to a tensor with only lower indices. Secondly, we can always break things up into a symmetric and antisymmetric part. Let's take a tensor of rank 2. I can break that up into a symmetric part, which I'll indicate by this, and an antisymmetric part. 1/2 xij plus xij, and 1 xij plus xji, and 1/2 the difference. The antisymmetric part, since it's only got two indices, and since they're 1 and 2, it must be proportional to the epsilon tensor. Definition of x, a scalar. Just like the trace of a symmetric tensor in a Lorentz group analysis was proportional to could be written in terms of a scalar. The part proportional to g mu nu could be written in terms of a scalar. Now, thus, if we have a tensor of mixed symmetry, we can always symmetrize it, and the antisymmetric parts can be written in terms of tensors of lower rank with fewer indices, with the epsilons taking up the missing indices. Thus, in fact, the only thing we have to look at, the only place as we systematically go through our catalog of bigger and bigger tensors looking for newer and newer representations, are symmetric tensors with fully symmetric tensors with only lower indices. Now, I can't think of anything else I can do to simplify those objects. There they are. They're just completely symmetric tensors with a bunch of lower indices. So I will guess. My guess is, which I'll try and verify, that the irreducible representations are generated by transformations on the space of tensors up to some number, which with malice aforethought I will call 2s, where 2s is an integer. Yes, Kay? Depends how you, sure, if you want me to put one there, I'll put one there. Which are completely symmetric under all lower indices, and 2s is S is 0, 1/2, 1, etc. That's a stupid notation from this viewpoint, but I adopt it so you'll see the connection with the standard notation for SU2. Now, the first question is, what is the dimension of these representations? How many I'll call the representation ds of U, a unitary unimodular matrix, or just for shorthand, S. So I don't have to keep writing D's and U's. Now, first question is, what is the dimension of S? That's the question of how many independent tensors there are with the desired symmetry properties. Well, since the tensor is completely symmetric, the only significant feature about a component is how many 1s it has and how many 2s it has. How they're distributed is irrelevant. That's what complete symmetry means. So the question is, if we have 2s objects and we want to put them in two boxes, how many ways are there of doing it? One box being indices 1 and the other box being indices 2. This is an easy thing to do. We imagine the two S objects are written out on a line. There are two S of them. I've done the case S equals 5/2. And no, S equals 3, I see. Then I imagine I have a wall. I'm going to put the wall down someplace in between. Everything to the right will be a 1. Everything to the left will be a 2. That's the two boxes. There are obviously 2S plus 1 places I can put the wall, starting from all the way over here to all the way over there. So the dimension of S is 2S plus 1. Are there questions?
Why are there two boxes?
1 is the number of indices that will be 1, and the other is the number of indices that will be 2.
Why is there one and
Because it's SU2, and all I can be is 1 or 2. Okay, is that a clear answer? For SU3, there'll be 3 boxes in the corresponding computation. Now, so that's the right dimension counting. That looks pretty good. We've seen that 2S plus 1 where S is a half integer before. Let's count the isospin, the I sub z content of these representations. Okay. For the subgroup of I sub z rotations only, we know how I sub z rotations fit into the isospin group. E by angle theta. U equals e to the I theta over 2. I put in the over 2 because of, again, a dumb convention that it's an isospin rotation by 4 pi that gives you back the identity for a general representation. We all know that. That's how you embed I sub z rotations in SU2. You observe it as a unitary matrix of determinant 1. That's just saying the proton has isospin 1/2 and the neutron has isospin minus 1/2. Thus, if I'm to make an I sub z rotation for this particular U, and if I take a tensor component which has a bunch of 1s, say R of them, and then a bunch of 2s, of course 2s minus R of them. That thing is just going to be unchanged. Every 1 will give me a factor of e to the I theta over 2. And every 2 will give me a factor of e to the minus I theta over 2. So that just gives me e to the I theta over 2 times R minus 2s minus R equals e to the I theta R minus S. Now R can go from 2s plus 1 to 2s minus 1, from 2s plus 1 to 0 by integer steps, being an integer, the number of indices. And therefore I sub z equals S, can go from 2s to 0 by integer steps, since there are no more than 2s indices. I sub z equals S, S minus 1, S minus 2, down to minus S as R runs through its range. This is, of course, the correct I sub z content of a representation of SU2. Is everybody happy? So all clear. Okay. I mean, the representations of SU2 are no great triumph, but I just want to show you these methods work. Let's work out out an actual example, let's work out how the field theory of pions and nucleons would look in this notation. The pions are, of course, as we know, isospin 1. The nucleons are isospin 1/2. Therefore, we begin by the representation 1/2. Which is supposed to be the nucleon field. Instead of calling it X, I'll now call it N. It's the nucleon field with space and Dirac indices suppressed. Ni goes into Uij Nj. Equivalently, if I write the nucleon field as a two-component row vector, proton and neutron, instead of one and two component, giving them their familiar names, this can be written as N goes into Un. This could either be the proton and neutron field, which is how I'll think of it for most of the time, or it could be the proton and neutron states with their momentum and spin variables replaced. It doesn't matter as far as the SU2 transformation properties go. The conjugate fields transform according to the conjugate representation. I will call them n bar and write them as a column vector. And they get the conjugate matrix, so n bar goes into n bar U adjoint. The definition of the conjugate representation gives me the complex conjugation, and the fact that I write the vector on the left rather than the right switches the indices and gives me the adjoint. Thus, for example, an invariant, the obvious invariant we make to make an invariant Lagrangian is, for example, n bar id slash minus mn, which is manifestly SU2 invariant. No excitement at this stage. A side remark, because of the existence of the invariant epsilon tensor, I can make an object that transforms like a column representation, like a row vector out of a column vector by using the epsilon tensor. That is to say, I could define n upper I equals epsilon ij n lower j. And although that wouldn't involve the conjugate fields, it would transform like a row vector. It would transform just like the conjugate fields. And because the epsilon tensor is epsilon 1, 2 is plus 1, that would have neutron here. But epsilon 2, 1 is minus 1, so that would have minus proton here. That's the reason why when you build an isospin invariant 2-nucleon state, an isosinglet 2-nucleon state, it is, of course, proton-neutron minus neutron-proton. It's the minus sign from the epsilon symbol that is doing the job, not plus. It's p bar p plus n bar n, but it's pn minus np. You either complex conjugate to raise the index, or you multiply by the epsilon tensor to raise the index. Now, let's go on to the pions, or the sigmas, or any other system with isospin 1. My eye will be focused on the pions, and that corresponds to a symmetric tensor with two indices. Equivalently, and it turns out to be more convenient to do it this way, one can raise one of the indices using the epsilon tensor and write this as a mixed object. My freedom. Of course, the mixed object is no longer symmetric, but it still has a constraint in it. It is traceless. As you see by summing the indices here, this object is symmetric and this one is antisymmetric. Because we've raised an index, this transforms like the outer product of one row vector and one column vector, and therefore under the action of U, I can write things in simple matrix form. Phi, a 2 by 2 matrix, goes into U phi, U adjoint. This transforms just like the product, not the product of row times column, which is a scalar, but the product of column times row, which is an object with two indices. We can also identify how this 2 by 2 matrix phi looks by thinking of multiplying Pn times P bar n bar and working out what each of the individual components is. That's a typical two-index object, one lower and one upper. Let's see what happens. In the 1-1 object, if we do things this way, a remark I should have made, it is obvious that it's consistent with the group to impose the condition that phi equals phi adjoint. I'll do that for the pions because I want 3 real fields, which corresponds to a traceless 2 by 2 Hermitian matrix. If I were doing with the sigmas, where I'd want 3 complex fields, I wouldn't do it. Onwards. Up here, we have PP bar, which is an object that carries isospin 0, and therefore this must be some number times a neutral pion field. Down here, we have Pn bar, or up here, Pn bar, which is an object that carries positive plus 1/2 isospin, so it must be some multiple of the positive pion field, and I'll just call that phi plus, since how I scale my fields is a matter of taste. Down here I must have the conjugate object, the negative pion field, and by tracelessness, down here I must have alpha phi naught. How I fix alpha is again a matter of taste, but of course I can normalize any one of my independent dynamical variables any goddamn way I please. But it's convenient to make one-half trace phi squared an obvious invariant under this operation, under the SU2. Is equal to, I get phi plus phi minus twice, so that's phi plus phi minus, plus 2 alpha squared phi naught squared, one from here and one from here. And since I'd like to, if I want I know that the SU2 symmetric mass term in my other way of thinking of things was phi plus phi minus plus 2 over 2. Excuse me, I forgot my 1/2. I put it in here, but not here. Plus 1/2 phi naught squared, 1 for a complex field, 1/2 for a real field. I'll choose alpha equals 1 over root 2. So the mass term will come out all right. I'll do that by erasure. And that's just a convenient normalization of the pi naught field, so it will be conventionally normalized in the mass term. Therefore, also in the kinetic energy. Therefore, the kinetic energy, or the whole Lagrangian for the pion, can be written as 1/2 trace d mu phi, the 2 by 2 matrix, d mu phi, plus mu squared over 2 trace phi squared, and that will just end up, when one does all the traces, being our conventional form. And we've written it in a way so that it's manifestly SU2 invariant. Okay, any questions? The nice thing about doing things this way is that it's easy to write down the coupling that is manifestly SU2 invariant. Of course, it was easy for us before, but don't forget last year you spent 2 weeks working out the Clebsch-Gordon coefficients for the rotation group. But here we can do it in a line. We have a matrix, phi. We have a row vector and a column vector, the nucleon fields and the anti-nucleon fields. We want to form an object that is an SU2 scalar. It's very easy to see what that must be if we're talking about Yukawa couplings. That's, of course, irrelevant from the viewpoint of SU2, but as a purist, I put it in. There it is, the product. Row vector, matrix, column vector. A scalar. The u's here, cancel the u adjoints here, and the whole thing is obviously invariant. Any questions? Yes?
Did you show that these representations are irreducible?
No, we showed that last year. I mean, for SU, here I base my prior, I'm using prior knowledge of SU2. Next lecture, when I begin SU3, I'll, of course, since you don't have prior knowledge of SU3, have to work to show they're irreducible. I will work, and I will show they are irreducible. Yes?
This way of thinking of the matrices is equivalent to dotting in the generators with some column of the final one?
Yeah. Well, you can see it's exactly the same form. All those 1 over square root of 2's that we got last semester in the isospin invariant interaction just come out here. Here's the 1 over square root of 2. Okay, it's phi plus n bar p, p bar n, plus phi minus n bar p, plus 1 over the square root of 2, phi naught p bar p, minus 1 over the square root of 2, phi naught n bar n. Okay, it's the same thing. It's got to be the same thing. There is only one SU2 invariant Yukawa interaction. Since both methods are right, both methods must give the same result. You see how the square root of 2's here come from, it looks completely different. Instead of fiddling with raising and lowering operators, just comes from the condition that I want the trace of the square of the matrix to be properly normalized. But they're the same square roots of 2's. Likewise, of course, the phi-4th interaction is trivial. Trace phi squared, quantity squared. Now, this completes what I want to say about SU2 in this matrix and vector way. It is obviously inferior to the other way of doing things, because it's nice if you're playing with isospin 1/2 and isospin 1, but when you start going up to isospin 3/2, you've got a 3-index tensor. You can write it as a 3-index tensor, that's for sure, but there's no nice matrix way of writing a 3-index object. However, it's useful. Firstly, the tensor way is completely general with all those indices and is indeed used. It's van der Waarden's method of treating the Lorentz group, where he, as a product of SU2's cross SU2's, where he has two kinds of indices called dotted and undotted, much used in the literature. And secondly, even the matrix trick is nice if you're only worrying about certain selected representations of low dimensionality, which will be our situation with SU3. Now, may I run on for 5 minutes more just to give the starting point of SU3? I'll give the starting point, and then I'll develop all the properties next lecture. Everything is the same except the epsilon tensor has 3 indices. That makes all the difference in the world. For one thing, we can't make the epsilon tensor do as an ersatz metric tensor to raise and lower indices. We can lower an index with it, but then we raise the rank of the tensor by 2, which is bad show. Therefore, we have to, on the other hand, we can still, given an antisymmetric tensor, write it as epsilon ijk xk, a familiar trick from three-dimensional real orthogonal group where one writes an antisymmetric 3×3 matrix as a polar vector, or an axial vector, excuse me. Therefore, we can get rid of antisymmetric parts blithely, reducing them as we go up to tensors of higher and higher rank to objects of lower rank, which we have presumably already investigated in our iterative procedure. But we cannot get rid of upper and lower indices. We're going to have to live with both of them. Therefore, the sort of object we arrive at, straining our ingenuity, is a tensor with m upper indices, n lower indices. It's completely symmetric up here. It's completely symmetric down here because we can always get rid of the antisymmetric part using epsilon. And since summing on indices is an invariant operation, we can arrange so that it is traceless, and that is to say, if you sum any upper index and any lower index, you get 0 by subtracting out a bunch of terms proportional to delta. That's all I can think of doing, generalizing what I did for SU2. I thought hard, take my word for it. That obviously defines a representation. They may or may not be reducible. They may or may not be irreducible, but there they are. I have defined a representation. How the group acts on all tensors with m upstairs indices, n downstairs indices, and no trace anywhere in between. Thus, I have defined a representation which I will call dnm of u, or for shorthand, nm. In this next lecture, I will call these representations for short IRs. You are allowed, indeed you are encouraged, to think of IR as an acronym for irreducible representation. However, I will not prove they are irreducible representations until the end of next lecture. They are nevertheless a set of representations, and in the next lecture, I will deduce their properties, their dimensions, their isospin content, what happens when you multiply them together in an analog to the matrix tricks we saw here, and then finally prove that they are in fact a complete and an equivalent set of irreducible representations, thus putting SU2 on your knowledge of SU3 on the same solid footing your knowledge of SU2 is on at this moment. That is reserved for next lecture, and then the lecture after that I will give 40 applications. 4. Carried away by my enthusiasm.